Welcome everybody to this breakout session on nuclear propulsion, where we'll be providing an overview of nuclear propulsion in shipping with an extra focus on emerging technologies and business models. My name is William Cunningham, and I'll just kick off with some practical information. We'll have a presentation which will last about 25 minutes, and this will be followed by a question and answer session afterwards. Please put your questions in the chat, and I will monitor these and pick them out and put them to our expert towards after the presentation. With that, I will introduce our presenter today. His name is Ole Christen Reistad. He's a senior principal researcher at DNV's Research and Development Department, and is also an adjunct professor at the University of Oslo's Nuclear Research Centre. He is also lead author of DNV's recent white paper, Maritime Nuclear Propulsion, Technologies, Commercial Viability and Regulatory Challenges for Nuclear-Powered Vessels, which you can download at any time. I'll put a link to that in the chat after. With that, Ole, the floor is yours.
Thank you, William. Hello, everybody. Ole Reistad here, and I will do the presentation on the white paper on nuclear propulsion for ships. I'm very glad to pull into some of the continued thinking and deliberations we are doing on this topic. First, the backdrop. Nuclear is really then seriously considered as a viable solution for ship propulsion. And for one like me that's been engaged in propulsion on ships for decades, this is really interesting. And the obvious advantages with the stable, predictable energy cost, enhanced operational flexibility, higher speed, and I must say a different infrastructure than the traditional bunker is of course very important in addition to the zero emissions. But at the very beginning we can go a little bit behind those advantages really, because we can also kind of take forward some important trends in addition to decarbonization, as we have already taken up with the zero emissions, because the automation of technology and the digital revolution is really fundamental for being able to address mobile nuclear power at this stage. For one like me that's been living with nuclear for some decades, we have always felt the need and the IEA monitoring system around us, and to really be able to have the framework needed for nuclear is something that the developments in digitalization and automation is providing. Also, that we have come to a stage in nuclear where this technology is really more mature, and I would maybe come with a contested claim, but more public acceptable than it used to be. We see that, for example, in the European Union, it seems to be some convergence on what is safe nuclear energy. How safe is safe enough? And this more mature level of safety is a very important basis for being, for nuclear energy to be relevant in shipping. Public acceptability is really fundamental for also the DNV effort in this area. Everything starts and ends really with public acceptability when it comes to nuclear power. So these are trends that we have are considering and that we are taking as a starting point for our effort in this area. We are seeing more tangible results or happenings in this area also now. For in our own field and in our own company, we have completed approval in principle of the KSOE, the Korean shipyard's proposed design for a nuclear-powered container ship. And this was really an important occasion that took place in October last year. And we see here then KSOE together with our own technical director, Mr. Dugstad, which presented it as a DNV nuclear conference that we had in Korea last year. The technology developments, because we can take the issue of safety one step further and really dig into the small ball that is being displayed in the middle of this slide, the TRISO fuel. Because in this technology, you really build in the barriers and the safety within the innermost structure of the nuclear installation. And this is I would say, an interesting development, even if we cannot say that we have finalized the deliberation around the use of such type of fuels, but they represent an interesting development, a trend when it comes to safety, but also a development about making the facilities smaller and more compact, where you build in the barriers into the innermost structures. And we can also point to the DNV white paper. I can reveal that at the last time DNV were considering a white paper on the topic was in March 2011. And as we all know, something else happened in March 2011 in the nuclear business. Then we had the Fukushima accident. And then the issue really disappeared for some time from the headlines. So we see also some specific issues leading us and others to be more bold in their activities and in the level of detail that we are looking at this. So let's dig into some of the details and some of the thinking, because we just need a way to look at this that are contribute to organizing our thoughts around this. And while everybody kind of recognized that technology is in the midst of this, the framework, the regulatory framework, the international framework with international agencies and national regulatory authorities is of course important, and I will touch a little bit upon that later. But one other very important point is really the business models. And as we are preparing the coming periods research programs, we have identified business models as a very relevant topic, because nuclear is really introducing some different way of running these vessels, and the ship owners and the yards need to be aware of those requirements, because they may be other way to look at this than is the case today. So we'll start a little bit with the technology. Then going from the overall goal that having a public acceptable technology, we are looking into different types of technologies in this area. And I can say for sure that we are not ready to leave the good old pressurized water reactors completely out of the pictures. The newcomers in this area is really the high temperature gas reactors and the molten salt fast reactors. They have some a different timeline than the pressurized water reactors, but even for the traditional pressurized water reactors, some development are needed, because if you really are going to deploy these reactors into ports around the world, we have to really be able to see these reactors have a different level of impact or consequences in case of accidents. The business models or how to run these reactors may be different, and the potential for running the newer reactors in a more efficient way than the existing pressurized water reactors is really there. Then, if we really look to scaling and fabrication offsite or in the fabrics, reactor fabrics, so to say, the heat pipe reactors. A heat pipe reactor is really interesting. Heat pipe reactor is a reactor without movable parts. It's a small reactor. They have mostly been considered for space purposes so far, and to a certain extent, it is somewhat of the same capabilities that we are looking for in the maritime area. So these have come to the forefront after a long time being almost forgotten. We also see that it is really two distinct avenues between going for the thermal reactors. Thermal is really the traditional reactor technology, and the fast reactors. A lot of actors are really looking towards the fast reactors because they are more compact and represent really a more flexible type of reactor. But at the end of the day, it's very important that the shipping companies are coming forward with their needs and how they look to operate these reactors. And that is what we are really lacking now. Because to really be able to look at these technologies, and only by looking at the technologies to say what type of technology that fit for the maritime propulsion is not possible. And this have to be really combined with the purpose and the shipping segment, I would say. In that respect, I will put your attention to a topic that we think is important. And that is really the area of micro reactors, because a lot of people are considering SMRs in this area. And here you see two SMR reactors in this slide. You see the NuScale reactor, a water-cooled pressurized reactor, 60 megawatt electric. And you see the helium-cooled XC100 reactor that is now being produced for some of the Amazon data centers in the US, 75 megawatt electric. And to a certain extent, they seem very fit for purpose, but it's rather big installations. And micro reactors really represent a distinct area of reactor technology. So we are looking at micro reactors in particular because for the really small reactors, the standardized approaches are really more feasible to think about. And the emergency preparedness organization and systems associated with micro reactors are fundamentally different from the SMR technology that to a certain extent are just small big power reactors. The distinct differences are coming when you are having the micro reactors. So also the serial production and modular installations. In our case, we are of course thinking about yards, are really looking more feasible when it comes to the micro reactor area. So in that sense, it's important to consider maybe a distinct different type of reactors than the one you are following in the everyday news, because it's a lot of talk about SMRs these days, in particular as to many they look like a more realistic option for land-based energy than the large scale, maybe, definitely not modular 1,000 megawatt power reactors. So we could also take a step back and then look at the different technologies, how they play out in the SMR field, as is pointed out in the lower pictures here. Because while Russia and China each have launched their small and modular reactors, we are expecting the land-based energy reactors in the SMR area to come online in 29, 30, 31 with different technologies. The one we have mentioned with thermal, mostly thermal facilities, and then the fast technology also a little bit later. But if we look at this, the nuclear future on land with SMRs, with the new technologies, all with AI as a major driving force behind several agreements on the design and construction of these reactors, we may expect a parallel development on micro reactors. We already see it with the nuclear company Hadron in the US, where kind of the comparative advantage for them is really that they have a small reactor. They are considering a small and versatile land-based reactor. But we also see some initiatives for a similar thinking towards sea-based or maritime reactors. So we see the schedule here, 29 to up to 33 will maybe be the time where we can expect to see a prototype, a land-based maritime prototype for a propulsion micro reactor. A little bit earlier, maybe for a floating power reactor, but this is some indications, and so this will happen then really in parallel with what we expect to be the SMR developments. And let's take one case of this, and this is the high temperature gas-cooled reactor. You saw on one of the previous slides that this had a rather big and maybe bulky construction, and that's really related to the use of gas. That really provides us with some the use of some additional space combined with or compared with other type of coolants. But this also gives us some advantages related to the power density, and then to advantages in the sense that we may have a little more leeway on in the safety area. And if safety is of paramount importance, really the combination of an efficient reactor with a high level of inherent safety, where we also have some existing experience. A number of countries have really some experience with gas-cooled technology, and with the potential of using this advanced fuel, trisom fuel, we may start to see at least the contours of a maritime nuclear technology program. The fuel supply is limited, but that is really the case for all types of fuel that can be used in maritime reactors, except for the traditional PVR. But then we have other issues. But it is important safety issues that need to be considered here. You know, the use of gas, graphite, and with the possible intrusion of water is a bachelor level setup for an accident. So we need some development here really to be able to consider this as the serious or a probable option. But it is a serious contender, and that's why we're taking it forward here. When we look at the fuel cycle, the reactor is one thing, but when you look at the fuel cycle and the supply chain, we need a supply chain tailored for maritime use. And this needs to be developed as it needs to be developed for SMRs. So we have a number of issues that is related both to the front end, to the reactor technology, and the back end here. When it comes to the front end, it's really the enrichment services is a concern for reactors in general. And enrichment is a topic, is a area of work that is really limited to some very few actors out there. So then you have the development of fuel itself, the proprietary information related to fuel development. And for me, when I was operating a reactor, a big concern was really fuel, and to have qualified fuel supplies for, you know, beyond the next decade was really the normal topic. In the sense that that fuel is really so fundamental, so you want to be sure that you have assurances of supply of fuel. The back end has not been really considered in detail in most cases, but if you take, as we are doing in our effort, public acceptability as kind of the starting point for your effort, you must address this at an early stage. Thank you. So the issues, so we are then seeing some concepts coming forward here. We have already pointed to KSOE and their forward-leaning attitude about the reactor development and in a container ship, which was then presented last autumn. Of course, the most visible actor in this area is really Core Power, which is closest to promoting nuclear as a service for maritime energy supply. The concept from all seas with a standardized modular gas-cooled reactor is maybe closest to some of the elements that I have taken forward earlier in this talk. And if you combine that with a Dutch access to fuel and also an experienced regulator, you may have a powerful combination for being able to address all the aspects in the fuel cycle, as I was just touching on. So, but in total, it's really none of these concepts or models that have really addressed all the topics together. So we still lack to see a sustainable nuclear propulsion concept being presented internationally. So, but this starts and ends with deliberations on the price tag. The cost of electricity, or we all in the energy electricity business, we call it the levelized cost of energy, which is really a term to be able to compare cost, is really dominated by financing costs. So as you see in the left part of this slide, so the capital cost and the overnight capital cost is really the fundamental part. So it's really an important task to be able to do this, to build these reactors and ships in an efficient manner. DNV has been looking at costs, and we have been looking at the reactor costs and see that a reactor cost on $2,500 per kilowatt electric energy is really corresponding to where we have the fossil fuel today. In the white paper, we are elaborating on this because we see that some of the large-scale nuclear today is really close to $2,500 per kilowatt, but that is cheap large-scale nuclear. So we must be able to really hit the same levels of cost related to reactors, and then that's why these considerations on the potential for fabrication offsite or installation in a yard and modularization is so important and fundamental in the area of shipping. And we will continue to look at cost, because if you are looking at the historical costs in the different projects, and you're really looking at the overrun of recent land-based nuclear power plants, they can, to be frank, scare the shit out of anyone wanting to engage in this area. So it's really that repeatedly building one-of-a-kind facilities is maybe not the best way of increasing the efficiency. So it's really the re-engineering and the regulator approval loop has nearly been endless in some of these projects. So this is leading to poor learning rates and poor modularization. And even if we try to build the same facility several times, they are built in different countries, and the regulatory authorities are able to promote very different abilities, and thereby putting people or construction companies into this endless approval loop. And I can say so from my own experience, because I've been a regulator for many years, but then being an operator afterwards. Thanks. So this can be overcome in the maritime model, because we are talking about a shipyard-based industry, also when it comes to reactors here. The reactor equipment are one part of the cost here, but structure and buildings also constitute an important element of this. So it will be really different in a container ship, and we really need nuclear propelled vessel specific costs here. So we see that the mass production and standardization of SMRs offers some potential for significant cost reduction. Here we are we are looking especially at the elimination of rework, and experience and cross-site standardization are able to reduce nearly the price tag with over 50%, so to say. So it is some experiences from the SMR that should be applicable also to the maritime shipping industry, but the project has to come to more mature stage than we have seen so far yet. So a lot of our experience and knowledge and understanding and projections are coming from the SMR and large-scale reactors. And in that sense, it is a fair question to ask if maybe the maritime area, with its intrinsic potential for having modularization and standardization, maybe will form the basis for SMR. So then we had a power outage here at Høvik, and this is giving us a very good example on how to work with nuclear technology, because when DNV is addressing nuclear and nuclear safety on a ship, we some years ago started with dimensioning and looking at the power systems, because a blackout on a land-based power plant is really quite similar to how it is to operate a ship with a reactor. We are then reaching the end of this presentation, and going then from the pilot projects that we see now in the pre-phase to a recognized commercial fleet, we start to see a possible a way forward. And we are having the pre-phase now in the 20s, where we will use for understanding the cost, that we are establishing the framework. IMO just started its effort, and we are establishing the commercial propulsion projects, such as we have seen with Allseas. Then we will see a main phase here, going on from I would say 3 to 7 years ahead. We are filling in the framework that IMO will use some years to flesh out. And we may also start to see some infrastructure in the sense of yards and some port preparations. And also potentially see the start of some propulsion projects being started for implementation. We, at our conference in Korea last autumn, we really saw the KSOE be very clear about their intentions to have a design ready in 2030. And after that phase, we may then look at the new beginning in this area, where we are able to see a pilot some of the first projects seeing the day break, so to say, that we see the commissioning of the first international recognized nuclear commercial vessel. Our projection is 10 years from now, and that is really optimistic perspective. But the ability to really address systematically reactors of a reactors of a different type than the large-scale reactors, and in that sense, I really think about the micro reactors. At the same time as we are able to work on the harmonization of the international approach to safety, as is the task for the classification companies. While the shipping industry is maintaining its focus on the reduction of climate gases, we may see this emerge in a decade time. So thank you. I think that was really what we wanted to say at this stage. A little bit more colored by the forward-looking thinking. And again, I will really point you towards the white paper that was published last autumn. Many of these questions that we have raised today are coming forward in the text. If they are not explicitly put up there, you will find all the basis for them in the text in the white paper. Thank you.
Okay. Thank you, Ole. We are just dealing with a couple of technical difficulties here, but I think we can adapt pretty well. I think we have done. So I think we have time for a couple of questions at the end. Thank you all for listening as well. There was one here, Ole, that came up on the chat. Maybe you'd like to take it. And the question was, on the safe disposal of waste, how to prevent radioactive leakage and ensuring the safety of staff? Obviously, that's an important question.
Yeah, it's the question is really how spent fuel will be handled on these types of facilities. To a certain extent, again, we have to look back to one of the, I would say, trends that initially was taken forward here, because it is important that we, with these mobile reactors, we cannot have the type of access to the reactor during voyage as we have to reactors on land. So it will be a higher level of automation, so to say, or we will be relying also on some additional power sources that will really be part of the design in these cases, because we think it's hard to see that a total blackout, having no power sources whatsoever on a ship with a reactor is really acceptable.
Okay, very good. And staying on, I guess, the question of safety, another one from the chat here was, has TRISO been tested for contact with seawater? Is that something you've considered?
Yes, TRISO has been considered definitely with seawater, and in that respect, we have also some very good cases. Submarine cases laying at the bottom of the sea with a lot of seawater in them at the moment, and the leakage rate from these vessels is not very high, and so to say, it's a lot of radioactivity in seawater as it is out of natural reasons. So. But that is really one of the reasons why we are lifting forward the topic of TRISO fuel, because we think that the properties of fuel in seawater is really, really fundamental to really achieve the level of public acceptability. Not only must these vessels be able to salvage, as is a point in the nuclear code today, but it must be a scenario that is being considered that these are actually sunk and have to be and still have not to represent any unacceptable environmental uncertainty.
Okay, we are quite well over time. Maybe we'll have time for one more question, which we received earlier, and that was, why should we pursue the new technology of gas-cooled reactors when we already have existing PWR reactors?
Yeah, I did touch upon that a little bit, and the questions about PBR reactors is really it's really an interesting questions, because if you see on the manning of the Russian floating power installations and the Russian icebreakers, the level of manning is really beyond what we would think is realistic for a commercial vessel today. And in that sense, it's very important to have really a simpler facility to take care of, because these facilities with pressurized water reactors have a lot of systems that are working together as systems to maintain and follow up also during operation, and that requires people, with being trained for the purpose. And that will be a major point forward. How really to have an acceptable level of manning of the propulsion system with the reactor, at the same time as you're having an adequate level of competence available for the ship in case of accidents. And that, presumably, that has to be solved also through some available competence on land. So the idea or the concept of remote operating centers and how you look upon this is in the level of automated ships is very interesting and relevant. But the reactor vendors has to answer this, and at the end of the day, it's the shipping community itself that is coming forward with its requirements for these ships. So, and that is really the most important point, that the shipping community come forward with how this have to be if it shall work on a ship.
Okay.
Thank you.
Yes, thank you, Ole. I think that's a very nice note to finish on. This is all about the shipping community and everybody coming together collaboratively. We have a QR code here for download of the white paper. I will put another link in the chat here in case you don't want to use the QR code. So you can go straight to that link that I just put up there, and you can download the white paper, of course, for free, which is like any other DNV white paper. Thank you all very much for joining us today at this breakout session. Thank you very much for attending METS. It was great to see so many of you, and please feel free to get in touch with us at DNV at any time. We are ready to talk. Thank you very much. Goodbye.